There is a quiet brightness beyond the familiar stars of our sky. Nothing dramatic, nothing insistent, and yet it extends outward on a scale that challenges comprehension. So, just how large is the galaxy we call Andromeda? Welcome to the Sleepy Scientist. If you enjoy drifting through questions like this, you're very welcome to subscribe and join these quiet explorations, and if it's not too much to ask, do let me know in the comments where you're listening from. That subtle glow visible on a clear night has been known for as long as humans have looked carefully at the sky. For most of history, it was thought to be a cloud or a distant smudge of unresolved light, quietly fixed in place among the stars. Its apparent size seemed modest. Its boundaries appeared gentle and contained. Nothing about it suggested enormity. Modern astronomy has learned to be wary of appearances. As telescopes became more sensitive and observations more patient, Andromeda began to reveal layers that had never been seen before. Long exposures uncovered stars far beyond its bright spiral arms. Wide-field surveys traced faint stellar streams stretching outward like echoes of ancient motion. Measurements of how stars and smaller galaxies move around it hinted at mass extending far past anything that shines. With each improvement in observation, Andromeda seemed to grow, not suddenly and not dramatically, but quietly. Its edges softened, its outline blurred. What once looked like a neatly bounded island of stars became something far more diffuse, more expansive and harder to define. Astronomers discovered that asking how big Andromeda is depends on what is being measured. The luminous disk that first caught the eye, the vast halo of ancient stars surrounding it, or the invisible structure inferred through gravity alone. Each tells a different part of the story, and each expands the galaxy well beyond its familiar appearance. Some of the most significant discoveries came almost unintentionally. Surveys designed to study nearby stars kept finding Andromeda stars where none were expected. Projects meant to refine distances instead revealed structures hundreds of thousands of light-years across. Even the space between Andromeda and the Milky Way turned out to be less empty than once believed, threaded with overlapping regions that challenge the idea of where one galaxy ends and another begins. Over time, the question shifted. It became less about locating a clear edge and more about understanding influence. How far Andromeda's stars extend, how far its gravity reaches, how much space is quietly shaped by its presence. This is not a story with a single number waiting at the end. It is a slow unfolding of perspective, shaped by decades of observation and refinement. A reminder that in astronomy, size is rarely sharp, and boundaries are often suggestions rather than lines. Tonight's journey explores how Andromeda grew larger in our understanding, how careful measurement transformed a small patch of light into one of the most expansive structures in our local universe, and how, in the process, it taught astronomers something subtle about scale itself. Settle in. Let the galaxy expand gently outward. At the beginning of the 20th century, Andromeda did not yet feel enormous. It did not even feel like a galaxy. Through the telescopes of the time, it appeared as a soft, elongated glow. A misty patch of light stretched gently across the sky, brighter in the centre and fading outward into darkness. Astronomers referred to it as the Andromeda Nebula, grouping it with other cloudy objects whose true nature was still unclear. Some thought these nebulae were nearby collections of gas and dust, forming stars within the Milky Way itself. Others suspected they might be something far larger, but there was no way to be sure. The problem was not imagination, it was measurement. Early telescopes were limited by glass quality, atmospheric distortion, and the sensitivity of the human eye. Even when photography began to assist astronomy, the earliest photographic plates could capture only the brightest regions of an object. Anything faint, diffuse, or spread thin across the sky simply failed to register. Darkness swallowed it whole. So when astronomers pointed their instruments toward Andromeda, what they recorded was only its most obvious feature: a bright central region, a smooth glowing core, a disk that seemed well defined and comfortably contained. The outer reaches, where light thins and stars grow sparse, remained invisible. To early observers, Andromeda looked modest. Larger than most nebulae, perhaps, but still something that could plausibly fit inside the Milky Way. Its apparent size on the sky was measured in angular terms, how wide it appeared compared to familiar reference points. By those measures, it seemed manageable, finite, knowable. That impression shaped early estimates. Photographic plates taken in the late 19th and early 20th centuries captured Andromeda as a flattened oval of light. Astronomers traced its visible outline and assumed that what they could see represented most of what existed. This was a reasonable assumption at the time. After all, if something emitted light, and that light did not appear on the plate, how could it be there? The answer, it turned out, was patience. Photographic plates required long exposures. Early ones could take hours, sometimes nights, to collect enough light to form a clear image. Even then, they struggled with faint stars and low surface brightness regions. The human eye, peering through an eyepiece, fared no better. Vision adapts poorly to subtle gradients. Where light fades gradually, the brain often decides that nothing is there at all. As a result, Andromeda's bright core dominated attention. The outer regions were assumed to taper off quickly. Its size was underestimated not because astronomers were careless, but because the universe was quieter than their instruments could hear. The question of what Andromeda truly was came to a turning point in the early 1920s. Careful observations of individual stars within the glowing patch revealed something extraordinary. Some of those stars changed brightness in a predictable way, allowing their intrinsic luminosity to be estimated. Comparing that intrinsic brightness to how faint they appeared revealed their distance. The numbers were unsettling. Those stars were far too distant to belong to the Milky Way. They lay well beyond its boundaries, separated by distances that forced a dramatic rethinking. Andromeda was not a nearby cloud. It was an entire galaxy, comparable in scale to the Milky Way itself, containing countless stars of its own. With that realization, Andromeda suddenly grew. Not physically, of course, but conceptually. It was no longer a small structure tucked inside our home galaxy. It was a separate island of stars, adrift in the vastness between galaxies. Even so, its size was still underestimated. Knowing that Andromeda was a galaxy did not immediately reveal how large that galaxy truly was. The same observational limitations remained. Telescopes still captured mostly the bright inner disk. Photographic plates still missed faint outskirts. Astronomers now understood that Andromeda was vast, but they still did not know just how far it extended. Early size estimates focused on the luminous region, the spiral structure, where stars were densely packed and easily visible. This region appeared well defined, with graceful arms curving outward from the centre. Beyond those arms, the light seemed to drop away. It was natural to assume that the galaxy ended not far beyond that point. This assumption shaped diagrams, textbooks, and mental images for decades. In reality, those early measurements were like judging a city by its downtown alone. Bright, crowded and easy to see, but hardly representative of everything that lies beyond. The suburbs, the outskirts, the quiet regions where lights are sparse and distances stretch out, were missing entirely from the picture. The limitations of early instruments meant that Andromeda's faint stars blended into the background glow of the sky. The universe itself is not truly dark. Airglow, scattered light, and the combined shimmer of countless distant stars create a soft background that hides delicate structures. Against that glow, Andromeda's outer regions simply vanished. There was also a psychological element at work. Human perception prefers edges. It looks for boundaries and clean shapes. When a glow fades gradually rather than stopping abruptly, the mind often interprets the fading as an ending. Early astronomers, like all observers, were influenced by this tendency. Where the image became indistinct, they assumed the object had finished. So Andromeda was drawn smaller than it truly was. This underestimation persisted well into the middle of the 20th century. Even as telescopes improved, the focus often remained on the brightest, most photogenic parts of the galaxy. Spiral arms, star-forming regions, and the luminous core drew attention, while the faint outskirts continued to escape notice. Yet the seeds of revision had been planted. Astronomers now knew that appearances could deceive. They knew that galaxies were not neat, compact objects, but sprawling systems shaped by gravity over immense spans of time. The realization that Andromeda was a galaxy opened the door to a deeper question, one that would take decades to unfold. If the bright disk was not the whole story, how much lay beyond it? The early measurements of Andromeda, limited though they were, provided a necessary starting point. They gave astronomers something to build upon, something to refine. And perhaps most importantly, they taught a quiet lesson that would echo through future discoveries. What you see is not always what is there. As instruments grew more sensitive and observations more patient, Andromeda would begin to reveal just how incomplete those early views had been. The galaxy that once seemed modest and contained would gradually stretch outward, dissolving the idea of a clear edge and replacing it with something far more expansive. But at the beginning, it all started with a glow, a soft, misty shape, and a universe that was already far larger than it appeared. When telescopes left the surface of Earth, Andromeda changed again. Not because the galaxy itself altered in any way, but because the view finally did. For centuries, every observation of the sky had been filtered through the same restless layer of air. Earth's atmosphere bends incoming light, scatters it, and adds a faint glow of its own. Stars shimmer, edges soften, fine detail slips away. Even the largest ground-based telescopes were always listening through noise. Space-based observatories removed that problem in one decisive step. By orbiting above the atmosphere, they allowed light from distant objects to arrive undisturbed. What reached the detector was cleaner, steadier, and far more precise. When instruments like the Hubble Space Telescope turned toward Andromeda, the galaxy did not suddenly become brighter. It became clearer. One of the most important differences was time. Hubble was designed to stare. Instead of capturing a quick glance, it could remain fixed on the same region of sky for hours or days, collecting faint light bit by bit. Each photon that arrived was recorded and added to the rest. What could not be seen in a short exposure slowly emerged in a long one. This change alone reshaped Andromeda's appearance. Earlier images had shown a bright spiral disk, well-defined and elegant, fading neatly into darkness. Hubble's longer exposures began to reveal stars scattered beyond that familiar outline. At first, they appeared as isolated points, almost accidental. Then, as exposure times increased, they formed patterns, streams, halos, extensions that could not be ignored. The visible disk expanded, not abruptly, not dramatically. It stretched outward quietly, the way dawnlight spreads before sunrise. Each deeper image pushed the boundary a little farther, revealing that what once looked like empty space was in fact thinly populated territory. This process highlighted something fundamental about how telescopes work. They do not show objects as they are in some absolute sense. They show what light allows them to show, given enough time and sensitivity. Bright regions dominate quickly. Faint regions require patience. Andromeda's outer stars are faint not because they are unusual, but because they are spread across enormous distances. Their light is real, but diluted. Against the soft background glow of the universe, it sits right at the threshold of detectability. Hubble was especially well suited to this task. Its sharp vision allowed astronomers to distinguish individual stars in Andromeda, rather than seeing only a smooth haze. By counting these stars and measuring how their density changed with distance from the centre, astronomers could trace the galaxy far beyond its previously accepted edge. What they found was not a wall, it was a gradient. Star density declined gradually as distance increased. There was no sudden cut-off, no clear line where the galaxy stopped and space began. Instead, the light thinned, softened, and slowly blended into the background. This realization changed how astronomers talked about size. If a galaxy fades rather than ends, then its apparent size depends on how faint a glow the telescope can detect. A more sensitive instrument sees farther. A longer exposure reveals more. The boundary is not fixed. It moves with technology. Even with Hubble, that boundary remained provisional. As powerful as it was, Hubble still had limits. Beyond a certain point, Andromeda's stars became too sparse and too faint to separate cleanly from the background of distant galaxies and cosmic light. Noise began to compete with signal. Distinguishing what belonged to Andromeda from what lay far beyond became increasingly difficult. This meant that even Hubble could not see the galaxy in its entirety. That fact is easy to overlook when looking at its images. They feel complete, expansive, satisfying. But astronomers working with the data were always aware that what they were seeing was a lower limit, not a final outline. The galaxy was at least this large, possibly larger. This understanding encouraged new ways of thinking. Instead of asking where Andromeda ends, astronomers began asking how its light behaves with distance. How quickly does brightness fall off? How does star density change? How far does structure remain coherent before dissolving into the wider universe? These questions shifted attention away from edges and toward patterns. There was also a quiet lesson in humility. Every improvement in imaging had so far revealed more galaxy, not less. Each time astronomers believed they had captured Andromeda's full extent, deeper observations gently proved otherwise. This did not feel like failure. It felt like refinement. Space-based observatories had not exposed mistakes so much as assumptions. The assumption that brightness equals importance. The assumption that what fades must be ending. The assumption that galaxies are compact objects rather than sprawling systems shaped by gravity and time. Light does not behave that way. It weakens gradually. It thins. It disperses. Andromeda's visible disk, once thought to be a clean structure with graceful boundaries, turned out to be just the brightest portion of a much larger whole. A luminous center surrounded by increasingly subtle layers, each harder to detect than the last. There was even a touch of irony in this discovery. The better astronomers became at seeing, the less confident they became about defining limits. Clearer vision did not produce sharper edges, it revealed softer ones. Hubble's observations made one thing unmistakably clear. The size of a galaxy cannot be pinned down by a single image. It depends on depth, on patience, on how faint a signal the observer is willing or able to pursue. In that sense, telescopes do not simply reveal galaxies. They negotiate with them. They ask how much light is willing to be shared. They listen longer. They push deeper. And each time the galaxy answers with a little more than before. Andromeda, seen this way, is not an object with a tidy outline. It is a structure that slowly emerges from darkness, one exposure at a time. At first, Andromeda grew in the margins, not in images meant to impress, but in data meant to measure. As astronomers pushed beyond the bright spiral disk, they began to realize that the familiar picture of Andromeda was incomplete in a very specific way. Telescopes could now see faint stars, but only in narrow fields. Each observation was like peering through a keyhole. What was needed was not just depth, but breadth. The next shift came when astronomers decided to stop focusing on the center and instead map the space around it. Wide-field surveys changed the question entirely. Rather than asking what Andromeda looks like, they asked where its stars actually are. One of the most influential of these efforts was the Pan-Andromeda Archaeological Survey, designed not to take a single beautiful image, but to systematically scan a vast region of sky surrounding the galaxy. The goal was deceptively simple: identify individual stars that belong to Andromeda, even far from its bright core, and see how far outward they extend. To do that, astronomers relied on a particular kind of star, red giants. Red giant stars are especially useful because they are luminous and relatively easy to identify, even at great distances. Their brightness and colour follow predictable patterns, making them reliable markers of membership. If a red giant with the right characteristics appears in the outskirts of Andromeda, it is very likely part of the galaxy itself. When astronomers began plotting the positions of these stars across wide swathes of sky, something unexpected emerged. They kept finding them, far beyond where the disk was supposed to end. At first, these detections were sparse. A few stars here, a few there. It would have been easy to dismiss them as outliers or background confusion. But as the survey expanded and the data accumulated, patterns began to appear. The stars were not random. They formed a diffuse, extended structure surrounding the galaxy. Andromeda had a halo. This stellar halo was not a thin shell or a neat boundary. It was a vast, roughly spherical distribution of ancient stars, stretching far beyond the luminous spiral arms. In some directions, red giant stars associated with Andromeda were detected hundreds of thousands of light-years from the center. This alone changed everything. Earlier size estimates had focused almost entirely on the visible disk, which spans on the order of a few 100,000 light-years across. The discovery of the stellar halo effectively doubled that scale. Andromeda was no longer just a spiral galaxy with elegant arms. It was embedded within a much larger, more diffuse structure. Importantly, this was not a sudden announcement or a single dramatic paper. It was a gradual realization that unfolded as more of the survey was completed. Each new patch of sky added more points. Each confirmation strengthened the picture. The galaxy did not grow overnight. Understanding did. There was a quiet elegance to this process. Astronomers were not redefining Andromeda based on speculation or theory alone. They were counting stars, mapping positions, comparing densities. Where the number of red giants declined slowly rather than abruptly, the halo persisted. Once again, there was no sharp edge. The halo faded gradually, just as the disk had, but on a far larger scale. Its stars were old, often older than those in the spiral arms, relics of Andromeda's early history. Some likely formed in the galaxy itself. Others may have been acquired long ago, pulled in from smaller galaxies and stretched into long streams by gravity. These streams were another clue. Wide-field surveys revealed faint, elongated structures wrapping around Andromeda, the remnants of past mergers. They traced graceful arcs across the halo, evidence that the galaxy had grown not only by forming stars but by absorbing others over billions of years. Each merger added stars to the outskirts, puffing up the halo and extending the galaxy's reach. This made the concept of size even more slippery. Was Andromeda as large as its disk, as its halo, or as far as its oldest, most loosely bound stars could be found? The answer depended on perspective, but one thing was clear. Earlier measurements had been missing a significant fraction of the galaxy. There was also a methodological lesson embedded in these findings. Galaxies cannot always be understood by looking at light alone. The brightest regions tell only part of the story. The faint outskirts, though visually unimpressive, often carry the most information about growth and history. In a way, Andromeda had been hiding in plain sight. Its halo was not invisible. It was simply too subtle for earlier instruments and too spread out for narrow observations. Once astronomers widened their field of view and focused on individual stellar traces, the galaxy's true scale became impossible to ignore. The reaction within the field was not shock but recalibration. Size estimates were revised, models were adjusted, diagrams expanded, Andromeda's place among nearby galaxies was reconsidered. It was not just slightly larger than once thought, it was structurally more complex. This quiet expansion of understanding also reinforced a broader pattern in astronomy. Every time observation improves, galaxies tend to get bigger, not because they are changing, but because their faint components are finally being seen. There was even a touch of gentle humour among astronomers. Andromeda, it seemed, refused to stay inside the lines drawn for it. Each new survey extended those lines outward, as if the galaxy were politely reminding observers that it had never agreed to such boundaries in the first place. What mattered most was not the exact number assigned to its size, but the shift in thinking that followed. Galaxies were no longer viewed as compact islands of light surrounded by emptiness. They were recognized as layered systems with bright centers, extended halos, and long memories written in faint stars. By the time the wide-field surveys were complete, Andromeda had become something much larger than a spiral disk. It was a sprawling structure, shaped by time, gravity, and repeated growth. A galaxy whose most expansive parts are also its quietest. And all of this had been there all along. For a long time, Andromeda's spiral disk felt like the whole story. It is the part of the galaxy that announces itself most clearly. Bright, structured, elegant. From even modest telescopes, the disk reveals sweeping spiral arms wrapped around a luminous central bulge. Dust lanes cut dark curves through starlight. Star-forming regions glow softly, marking places where gas is dense and active. It looks complete, almost self-contained, as if the galaxy has been neatly drawn and carefully finished. It is easy to see why astronomers once thought this was essentially all of Andromeda. The disk is visually striking because it concentrates light. Stars are packed closely enough that their combined glow stands out clearly against the sky. Gas clouds reflect and emit light. Young stars shine intensely. Compared to the faint outskirts discovered later, the disk feels confident and well-defined. Early measurements naturally focused here. Astronomers traced the visible spiral arms and measured how wide they appeared. They mapped the bright regions where stars were easiest to count. Over time, these measurements became more precise, and disk size estimates began to settle into a consistent range. Unlike the halo, whose boundaries kept expanding as instruments improved, the disk seemed stable. It did not keep growing. This stability gave the disk an air of authority. If something was measurable, repeatable, and visually obvious, it felt reliable. Diagrams of Andromeda in textbooks often showed a tidy spiral disk with little emphasis on anything beyond it. The disk became the galaxy, at least in the popular imagination. But even as the disk's size stabilized, something curious was happening within it. Astronomers began measuring how gas moves inside Andromeda. Clouds of hydrogen gas emit radiation at specific wavelengths that radio telescopes can detect, even when the gas itself is invisible to optical telescopes. By observing how this emission shifts as different parts of the disk move toward or away from Earth, astronomers could measure rotation, This produced what are known as rotation curves. A rotation curve shows how fast different parts of a galaxy orbit its centre at different distances. If most of a galaxy's mass were concentrated in the bright disk, then stars and gas farther out should orbit more slowly, much like planets in the outer solar system move more gently around the Sun. That is not what Andromeda showed. Measurements revealed that gas far from the centre was moving faster than expected. Instead of slowing down, orbital speed stayed roughly constant across much of the disk. This told astronomers that the mass influencing motion extended well beyond the bright regions they could see. The disk was orderly, but it was not telling the whole truth. Still, the disk itself remained visually neat. Its spiral structure could be traced cleanly. Its thickness and radius were measurable. Compared to the diffuse halo uncovered later, it felt almost architectural. Clean lines, recognizable shape. A galaxy you could draw with confidence. This contrast turned out to be misleading. The disk gave the impression of completeness because human perception prefers structure. Spirals feel intentional. Symmetry feels finished. When light is concentrated into well-defined patterns, the mind assumes boundaries must follow soon after. But galaxies are not designed to satisfy intuition. The disk is only where conditions are right for stars and gas to gather densely and shine brightly. It is not where gravity stops. It is not where history ends. It is simply where visibility peaks. Beyond the disk, the galaxy becomes quieter. Stars thin out. Gas grows sparse. Structures lose their symmetry. Streams bend and twist. The neatness dissolves into something far more irregular, messy even. That messiness was invisible for a long time, not because it did not exist, but because it did not glow insistently enough to be noticed. In hindsight, the disk's very clarity worked against it as an indicator of size. Because it was easy to see, it was easy to mistake for the whole. Because its measurements converged early, it felt definitive. And because it behaved predictably in images, it encouraged the idea that Andromeda itself was similarly contained. Rotation measurements quietly contradicted this impression. The motion of gas within the disk hinted that much more mass lay beyond what the eye could trace. The galaxy's gravitational influence reached farther than its bright arms. Something unseen was shaping the disk's motion, holding it together and extending outward into darkness. Yet for years these implications remained abstract. The disk was still what people pointed to when they spoke of Andromeda's size. It was the part that could be shown, photographed, and compared. The messy outskirts were harder to visualize and even harder to explain. There is a certain comfort in tidy structures. They feel manageable. They invite confidence. Andromeda's disk offered that comfort, even as the data quietly suggested a deeper complexity. Over time, astronomers learned to separate familiarity from completeness. The disk is real. It is important. It contains a vast number of stars and much of the galaxy's visible activity. But it is only one layer, a bright, well-behaved layer sitting inside something much larger and far less orderly. In a sense, the disk is Andromeda's most convincing illusion. It looks like a boundary because it is where light gathers most strongly. It feels like an ending because brightness drops beyond it. But neither impression reflects the true extent of the galaxy. The neatness of the disk made it an excellent starting point. It also made it a poor guide to the galaxy's full scale. Only when astronomers looked past that neatness did Andromeda begin to reveal just how much more there was. At first, the stars appeared where no stars were supposed to be. They showed up quietly, at the limits of deep observations, scattered far beyond Andromeda's bright spiral disk. Individually, they were unremarkable, old, dim, easy to overlook. But taken together, they began to tell a story that reshaped how astronomers understood the galaxy. These stars belong to Andromeda's stellar halo. The halo is not a structure that announces itself. It does not shine brightly or form graceful patterns. It is diffuse, extended, and sparse, made up of stars spread across enormous distances. For a long time it remained hidden simply because it did not glow strongly enough to stand out. Deep star counts changed that. By carefully counting individual stars across wide areas of sky, astronomers were able to trace Andromeda's population far beyond the visible disk. Red giant stars again played a key role. Their predictable brightness allowed researchers to identify them reliably, even when they were scattered thinly across space. As these surveys expanded, the scale of the halo became impossible to ignore. Halo stars associated with Andromeda were found at distances exceeding 600,000 light-years from the galaxy's centre. In some directions they stretched even farther, dissolving gradually into the surrounding space. This was not a narrow shell or a tidy boundary. It was an enormous extended envelope of stars surrounding the galaxy like a faint mist. This discovery alone transformed earlier size estimates. If Andromeda's disk had once defined its scale, the halo redefined it entirely. The galaxy was no longer measured only by where its light was brightest, but by where its stars still belonged gravitationally. Including the halo effectively doubled the galaxy's known extent. And this was not speculation. These stars were not random background objects. Their distances, motions, and properties matched what would be expected of Andromeda's population. They were part of the system, even if they occupied its quietest regions. One of the most revealing clues came from metallicity. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium within a star. Stars formed early in the universe tend to have low metallicity, because heavier elements had not yet been widely produced by generations of stellar evolution. When astronomers measured the metallicity of Andromeda's halo stars, a clear pattern emerged. These stars were old, very old. Many had formed early in the galaxy's history, long before the spiral disk took on its present form. Some of these stars likely formed within Andromeda itself during its earlier stages. Others were probably acquired later, pulled in from smaller galaxies that wandered too close and were gradually torn apart. Their remains were stretched into long, faint streams that now lace the halo. The halo, it turned out, was a record of Andromeda's past. Every faint star carried information about how the galaxy grew. Each stream marked a merger long completed. Each metallicity measurement added a piece to the timeline. The halo was not just large, it was ancient. As surveys pushed farther outward, another subtle realization followed. Andromeda's halo does not exist in isolation. The Milky Way has a halo of its own, similarly extended and similarly diffuse. And when astronomers mapped the outskirts of both galaxies, they found that these halos overlap. The space between Andromeda and the Milky Way is not empty. It is shared. This overlap does not mean the galaxies are colliding in any dramatic sense. It means their gravitational influence extends so far that their outermost stars occupy the same broad region of space. The boundary between them is not a line, but a transition. In this shared territory, it becomes difficult to say where one galaxy ends and the other begins. This was a quiet but profound shift in thinking. Galaxies were no longer separate islands surrounded by emptiness. They were expansive systems whose outskirts blended together. Their influence reached far beyond their bright centres, overlapping gently with their neighbours. Brightness once again proved to be a poor guide. The stellar halo is faint precisely because its stars are spread so widely. Their combined light is thin, diluted across vast volumes of space. To the eye, and even to many telescopes, this looks like nothing at all. But the stars are there, moving slowly, bound by gravity, tracing out the true scale of the galaxy. This realization forced astronomers to rethink the idea of an edge. If a galaxy fades gradually rather than stopping, then its edge is not a place. It is a concept, a region where membership becomes ambiguous, where stars are few, and where definitions grow soft. Andromeda does not end where brightness ends. It continues quietly outward. There was a certain elegance in this conclusion. The most expansive parts of the galaxy are also the least conspicuous. The halo does not dominate images or capture attention. It requires patience, careful measurement, and a willingness to look where nothing obvious appears. Even then, it never fully reveals itself. Its outer limits blur into the larger structure of the local universe. Its stars thin until counting becomes uncertain. Its influence weakens until it blends into the gravitational background shared with other galaxies. This does not make the halo less real. It makes it more honest. The discovery of Andromeda's stellar halo marked a turning point. Size was no longer defined by what could be seen easily. It was defined by what could be traced, inferred, and understood through careful observation. The galaxy that once seemed neatly contained within a spiral disk was now understood as a layered system, bright at the centre, diffuse at the edges, vast beyond intuition. And perhaps most importantly, this discovery reframed what it means to belong. A star does not need to shine brightly to be part of a galaxy. It only needs to move with it, to share its gravity, to carry its history. In Andromeda's halo, those quiet stars do exactly that. Once Andromeda's true extent began to come into focus, a new question followed naturally. How many stars does something this large actually contain? It is an inviting question, and also a misleading one. No astronomer has ever sat down to count Andromeda's stars one by one. Even the most powerful telescopes can only resolve a fraction of them, and only in carefully selected regions. The galaxy is simply too vast, too distant, and too densely populated for a direct census. So astronomers count stars without counting them. The method begins with something that sounds deceptively simple. Instead of asking how many stars there are in total, astronomers ask how many stars of a certain brightness can be seen in a small, representative patch of the galaxy. That patch is chosen carefully, avoiding unusual regions and focusing on areas that reflect typical stellar populations. From there, the work becomes statistical. Stars are not all the same. Some are large and bright, others are small and faint. Most fall somewhere in between. Importantly, faint stars are far more numerous than bright ones, but also much harder to detect. Even with space-based telescopes, many of Andromeda's stars are too dim to be seen individually. This is where luminosity functions come in. A luminosity function describes how many stars exist at each brightness level. By measuring how many bright stars are visible, and understanding how stellar populations tend to be distributed across brightness, astronomers can infer how many faint stars must be present as well. It is not a guess, it is a structured extrapolation. Astronomers build these functions using well-studied regions where stars can be observed in detail. They then apply the same distributions to similar environments elsewhere in the galaxy. By scaling up from small, observable regions to the full volume of Andromeda, they can estimate the total number of stars it contains. The result is a number that feels almost unreal. Many studies suggest that Andromeda contains on the order of 1 trillion stars. That is roughly 10 times the commonly cited estimate for the Milky Way, though even that comparison comes with substantial uncertainty. This number tends to attract attention, but it deserves careful handling. 1 trillion is not a precise count. It is an approximation shaped by assumptions about stellar populations, the faintest stars, and how evenly stars are distributed across the galaxy. Change those assumptions, and the number shifts. That variability is not a weakness. It is an honest reflection of the challenge involved. Some estimates arrive at slightly lower totals, others push higher. The differences depend on how much weight is given to the faintest stars, how extended the halos assume to be, and how stellar density changes with distance from the centre. Each of these factors introduces uncertainty. What matters most is not the exact figure but the scale it represents. Andromeda is not just slightly more populous than the Milky Way. It operates in a different numerical regime. Hundreds of billions of stars at a minimum, possibly closer to 1 trillion, each one a sun in its own right, with its own history, lifespan, and eventual fate. Even arriving at that range requires careful restraint. Astronomers avoid overconfidence here for good reason. Luminosity functions rely on models of stellar evolution. They depend on assumptions about how many low-mass stars form compared to high-mass ones. They assume that regions not directly observed behave similarly to those that are. These assumptions are well tested, but they are still assumptions. Small changes ripple outward. If faint stars are slightly more common than expected, the total rises. If the halo contains fewer stars than inferred, it falls. The uncertainty grows as the galaxy itself grows. This is why star counts are usually presented as ranges rather than single values. The language is careful. Estimates suggest. Data indicate. Results are consistent with. There is a quiet discipline to this caution. Comparisons with the Milky Way are handled the same way. Our own galaxy's star count is also uncertain, typically estimated at a few 100 billion stars. Differences in structure, halo size, and star formation history make direct comparison difficult. The Milky Way and Andromeda are similar in some ways and different in others. Neither number is exact, neither needs to be. What matters is perspective. Counting stars without counting them allows astronomers to grasp scale without pretending to control it. It replaces the impossible task of tallying every star with a statistical understanding of how stellar populations behave. It trades precision for realism. There's also something quietly humbling in this approach. Even with modern instruments, Andromeda's stars resist full enumeration. The galaxy remains too large, too distant, and too subtle to be fully captured in numbers alone. Yet the estimates are still powerful. To say that Andromeda contains on the order of 1 trillion stars is not to boast. It is to acknowledge that the galaxy is an environment on a scale that stretches human intuition. The number is not meant to be visualized all at once. It is meant to recalibrate expectation. Each star contributes a small amount of light. Together they build the glow of the galaxy. Spread across a vast volume, their individual brightness fades, but their collective presence remains. That is why luminosity functions work. They respect the fact that most of the galaxy's content is faint, quiet, and easily overlooked. They allow astronomers to account for what cannot be seen directly by understanding patterns in what can. There is also a gentle irony here. The most numerous stars in Andromeda are the least conspicuous. Small, long-lived stars dominate the population, even though they contribute little to the galaxy's visual splendor. Bright stars capture attention, but they are rare. The galaxy's true weight lies in its quiet majority. Seen this way, star counts become less about numbers and more about structure, about how stars form, how they are distributed, how their collective behavior shapes what a galaxy becomes. Andromeda's immense star count does not make it special in a competitive sense. It makes it representative of what large spiral galaxies can be. It is a reminder that scale in the universe often hides behind subtlety. The galaxy looks calm, its light is gentle, but beneath that softness lies a population so vast that it can only be approached statistically. Counting stars without counting them is not a compromise. It is the only way to meet a galaxy on its own terms. For a while, Andromeda's size was discussed almost entirely in terms of light. How far the disk extended, how faint the halo became, where stars could still be seen. But light, it turned out, was only part of the story. As astronomers began to focus on how things move inside and around Andromeda, the meaning of size shifted in a fundamental way. Motion carries information that light alone cannot. It reveals where mass is, not just where stars happen to shine. The simplest idea is intuitive. Objects move faster when more mass is pulling on them. Measure how fast something moves, and you can infer how much mass must be present to keep it on course. Inside Andromeda, this approach began with stars and gas. Astronomers tracked how quickly material orbited the galaxy's centre at different distances. These measurements had already hinted that the visible disk did not contain all the mass influencing motion. Orbital speeds stayed high even where starlight thinned. But the most striking clues came from much farther out. Andromeda is surrounded by smaller satellite galaxies, each bound loosely by gravity. These companions move slowly, tracing wide, elongated paths through space. By measuring their velocities and trajectories, astronomers could estimate how much mass Andromeda must contain to keep these satellites from drifting away. The answer was unsettling. The visible stars accounted for only a fraction of the required mass. Even when the disk and stellar halo were included, there was still far too little matter to explain the observed motions. Something else was contributing. Something extended. Something invisible. This realization did not arrive all at once. It emerged gradually as more satellite galaxies were identified and their motions measured more precisely. Each new data point reinforced the same conclusion. Andromeda's gravitational influence reached far beyond the regions where stars could be counted. Velocity dispersion studies added another layer. Instead of tracking orderly rotation, these studies examined how stars and satellites move in many directions at once. The spread of their velocities, how much they differ from one another, carries information about the depth of the gravitational well they occupy. A shallow well produces gentle motion. A deep one allows faster, more varied movement. Measurements of velocity dispersion around Andromeda pointed to a massive, extended structure enveloping the galaxy. Once again, the mass implied by motion far exceeded what could be seen. This is where size began to mean something new. If mass extends farther than light, then the galaxy's effective size cannot be defined by brightness alone. Gravity does not stop where stars become faint. It weakens gradually, reaching outward into space, shaping the paths of objects that may never shine brightly enough to be noticed directly. In this sense, Andromeda's size is not just about where stars are located, it is about how far its gravity matters. That reach is enormous. Mass estimates derived from stellar motion and satellite dynamics suggest that Andromeda's gravitational influence spans well over 1 million light-years in radius. Some estimates extend it farther still. These figures depend on assumptions and methods, but they agree on one point. The galaxy's true footprint is vastly larger than its visible form. This does not mean that stars fill this entire region. Most of it is empty, quiet, and dark, but it is not uninfluenced. Objects moving through this space feel Andromeda's pull. Their paths curve gently. Their velocities reflect the presence of mass distributed across an enormous volume. There is a subtle shift in perspective here. Earlier discussions of size asked where the galaxy ends visually. Mass-based approaches ask where its influence becomes negligible. These are very different questions, and they yield very different answers. It also explains why earlier size estimates felt incomplete. They were focused on what could be seen easily, not on what could be inferred reliably. Light is compelling, but gravity is honest. This reframing helps resolve an apparent contradiction. How could Andromeda's disk look so tidy while its influence stretches so far? The answer is that disks form where matter settles into orderly motion. Halos, by contrast, are shaped by long histories of interaction, merger, and slow accretion. They are sprawling and diffuse, and their mass dominates the outer regions. From the inside, the galaxy feels structured. From the outside, it feels expansive. There is also a gentle lesson in restraint here. Mass estimates are powerful, but they are not exact. Different methods produce slightly different results. Satellite motions sample certain regions more than others. Velocity dispersion depends on assumptions about equilibrium and history. Astronomers know this, they account for it. Uncertainty is built into the conclusions. Even so, the overall picture is robust. Andromeda is far more massive than its visible stars alone would suggest. That mass is spread across a vast halo, extending well beyond the luminous disk and stellar halo traced by light. This has practical consequences. When thinking about Andromeda's interaction with its surroundings, mass matters more than brightness. Its gravity shapes the motion of nearby galaxies. It influences the structure of the local group. It determines how matter flows on scales far larger than the visible galaxy itself. Size, in this context, becomes relational. It is not about drawing a line around what can be seen. It is about understanding how far influence extends, how far orbits are shaped, how wide the gravitational conversation reaches. There is even a touch of quiet humour in this shift. After decades of refining images, extending exposure times, and counting ever fainter stars, astronomers realize that the most expansive part of Andromeda does not glow at all. The galaxy's greatest reach is invisible, yet it is felt everywhere around it. This does not diminish the importance of light-based measurements. They reveal structure, history, and composition. But mass-based measurements add depth. They transform size from a surface description into a three-dimensional concept. Andromeda is not just a spiral disk surrounded by faint stars. It is a massive system whose gravity quietly organizes space on scales that defy easy visualization. Seen this way, the galaxy's true size is not something you look at. It is something you move within, and that changes the question entirely. By this point, Andromeda had already grown far beyond its bright spiral disk and even beyond its visible halo of stars. Yet the most expansive part of the galaxy was still missing from view. It had never been seen directly. It had only been felt. Dark matter entered the story not as an exotic idea, but as a practical necessity. Astronomers were not searching for mystery. They were trying to make sense of motion. Stars, gas, and satellite galaxies were moving in ways that could not be explained by visible matter alone. Rotation curves provided the first persistent clue. As gas and stars orbit Andromeda's centre, their speeds reveal how mass is distributed. Close in, where stars are dense and light is strong, orbital motion behaves roughly as expected. Farther out, where light thins and stars grow sparse, something unusual happens. The orbital speeds do not drop off. They remain high. If only visible stars and gas were present, those outer regions should move more slowly. They do not. This pattern repeats not only in Andromeda, but in spiral galaxies across the universe. The implication is straightforward. There is more mass than meets the eye. Satellite galaxies reinforce this conclusion. These small companions orbit Andromeda at great distances, some hundreds of thousands of light-years away. Their motions are slow and wide, tracing long paths through space. Measuring their velocities reveals how much mass must lie within their orbits to keep them bound. Again, visible matter falls short. Even after accounting for the bright disk and the extended stellar halo, there is not nearly enough mass to explain what is observed. Something additional must be present, distributed broadly and smoothly across a vast region. That additional component is what astronomers call dark matter. Dark matter does not emit light. It does not absorb it. It does not glow, sparkle, or cast shadows. Its presence is inferred entirely through gravity. through how stars move, through how gas rotates, through how satellites remain attached to their host galaxies. In Andromeda, the dark matter halo dominates the galaxy's mass. This halo is not a thin shell or a compact structure. It is an enormous, roughly spherical distribution extending far beyond the visible galaxy. Estimates suggest that Andromeda's dark matter halo likely reaches out over 2 million light-years in diameter, perhaps more. This means that the galaxy's gravitational influence stretches far beyond where any stars can be seen, or even reliably counted. Importantly, this figure is not pulled from thin air. Astronomers combine observations with simulations to understand how such halos behave. Computer models are built using the known laws of gravity and the observed distribution of matter. These simulations are then tested against real data: satellite galaxy motions, velocity dispersions, the overall structure of the local group. When the simulated halos are too small, the satellite motions do not match reality. When they are too massive or too compact, the patterns diverge again. Only certain configurations reproduce what is actually observed around Andromeda. Those configurations consistently point to a very large dark matter halo. This process is iterative and careful. Simulations are adjusted, assumptions are tested, results are compared across multiple datasets. There is no single definitive model, but there is a growing consensus about the scale involved, and that scale is vast. At these distances, something else becomes apparent. Andromeda's dark matter halo does not exist in isolation. The Milky Way has a dark matter halo of its own, similarly extended and similarly dominant. When astronomers map the likely extents of both halos, they find that they already overlap. Long before any visible interaction occurs, the invisible structures surrounding the galaxies are intertwined. This overlap does not mean the galaxies are colliding in a dramatic sense. It means that their gravitational environments are shared. The space between them is shaped by both. Objects moving through this region feel the combined influence of two massive systems. In this context, the idea of a clear boundary becomes increasingly difficult to defend. Where does Andromeda end if its dark matter halo blends smoothly into that of the Milky Way? Where does one gravitational domain give way to another? The answer is not sharp, it is gradual. This uncertainty is not a flaw in the science. It is a reflection of how gravity works on large scales. Dark matter halos are not rigid containers. They are diffuse, overlapping, and dynamic. Their edges are defined not by walls, but by declining influence, by regions where gravity weakens enough that other structures begin to dominate. Astronomers are careful here. They do not claim exact sizes with false precision. Estimates of halo extent depend on assumptions about how dark matter is distributed, how satellites have evolved, and how the local group formed over time. Different models produce slightly different answers. Some halos are more extended, others are more compact. But all agree on the central point. The majority of Andromeda's mass lies far outside its visible form. This realization reframes everything that came before. The spiral disk, once thought to define the galaxy, is a bright island inside a much larger sea. The stellar halo, impressive in its own right, is still only a tracer of something more expansive. The true scale of Andromeda is written in gravity, not light. There is also a quiet restraint in how astronomers discuss this. Dark matter is not invoked to create wonder. It is invoked to restore consistency. Without it, the observed motions do not make sense. With it, they do. The concept persists because it works, not because it is dramatic. And yet its implications are profound. If Andromeda's dark matter halo extends over 2 million light-years, then the galaxy's effective size is measured not in where stars fade, but in where gravitational influence becomes negligible. That reach is enormous. It reshapes the structure of the local group. It influences how galaxies move, interact, and evolve. In this light, Andromeda is less an object and more an environment, a region of space organized by gravity, a vast invisible architecture within which stars, gas, and smaller galaxies move. Its brightest features are merely the most visible expressions of a much deeper structure. There is something quietly humbling about this conclusion. The largest part of the galaxy cannot be seen. It cannot be photographed. It cannot be admired directly. It must be inferred patiently, through motion and careful modelling. And even then it remains partially uncertain. Astronomers know the halo is there. They know it is large. They know it dominates the mass. What they continue to refine is its exact shape, its precise extent, and how it interacts with its surroundings. That uncertainty is not a gap waiting to be sensationalized. It is the normal edge of knowledge, a place where evidence narrows possibilities without eliminating them entirely. Andromeda's dark matter halo reminds us that size in astronomy is often hidden. The most expansive structures are the least visible. The greatest influences leave no light behind. The galaxy does not end where brightness ends. It does not even end where stars end. It fades into gravity. For many years, Andromeda was described as the larger sibling, the bigger spiral, the more massive neighbour. That comparison felt intuitive. Early measurements suggested Andromeda contained more stars, extended farther, and exerted a stronger gravitational pull than the Milky Way. The numbers seemed to support the story, and the idea settled comfortably into textbooks and popular explanations. But comparisons are only as good as the methods behind them. As astronomers refined their techniques, they began to realize that earlier contrasts between Andromeda and the Milky Way were not always made on equal footing. Different assumptions, different data sets, different ways of defining size. When those differences were accounted for, the gap between the two galaxies began to narrow. The first step toward a fair comparison was methodological consistency. When the same tools are applied to both galaxies, the results look more balanced. Disk sizes measured in the same way turn out to be broadly similar. Halo extents traced using the same stellar populations overlap in scale. Mass estimates derived from comparable satellite motions converge more closely than once thought. This does not mean the galaxies are identical. They are not. But it does mean that earlier claims of dramatic difference were often overstated. Take visible disks, for example. When astronomers compare the bright spiral disks using similar imaging depth and criteria, Andromeda's disk is somewhat larger, but not by an overwhelming margin. Both galaxies have extended spiral structures, dust lanes, and star-forming regions that taper gradually rather than ending sharply. Once measured consistently, their disks occupy comparable ranges. The same pattern appears with stellar halos. When red giant stars are used as tracers for both galaxies, the halos extend to similar distances. Each galaxy possesses a vast, diffuse envelope of ancient stars stretching hundreds of thousands of light-years from the centre. Differences remain, but they are subtle rather than dramatic. Earlier impressions of Andromeda's dominance often came from comparing its halo to an undersampled view of the Milky Ways. From inside our own galaxy, mapping the halo is more challenging. Dust obscures some regions. Perspective complicates distance measurements. As surveys improved, the Milky Way's halo grew outward in much the same way Andromeda's had. Once both were measured with comparable care, the contrast softened. Mass estimates followed a similar path. Early studies often assigned Andromeda a significantly higher mass, based on limited satellite data and simplified models. As more satellite galaxies were discovered around both systems, and as velocity measurements became more precise, mass estimates were revised. Recent analyses suggest that the total masses of Andromeda and the Milky Way are closer than once believed. In some models, Andromeda is slightly revealed to be more massive. In others, The Milky Way takes the lead. In many, the difference falls well within uncertainty. The important shift is not which galaxy is larger, but how sensitive the answer is to assumptions. How far the dark matter halo extends, how satellites are distributed, how equilibrium is defined. Small changes in these inputs produce different outcomes. Astronomers are well aware of this, and they treat the results accordingly. There is also a psychological factor at play. Andromeda is seen from the outside. Its structure is visible in a single frame. Its disk, halo, and satellite system can be surveyed directly. The Milky Way is experienced from within. Its shape must be reconstructed from countless individual measurements. That difference alone makes Andromeda feel larger, even when the underlying scales are similar. Perspective matters. Comparisons become even more nuanced when gravitational influence is considered. Both galaxies possess dark matter halos extending well beyond their visible stars. These halos overlap, sharing a broad region of space. In this context, asking which galaxy is larger becomes less meaningful. Their domains blend. The idea of competition fades quickly at these scales. Neither galaxy exists in isolation. Each has grown through mergers. Each continues to shape the motion of smaller companions. Each participates in the same local environment. Their histories are intertwined, even before any future interaction is considered. Methodology shapes conclusions more than rivalry ever could. When astronomers say Andromeda is larger, or that the Milky Way may be comparable, what they are really saying is that different definitions of size highlight different aspects of structure. Diameter emphasizes disks. Halo extent emphasizes ancient stars. Mass emphasizes gravity. Each tells a valid story, but none tells the whole one alone. This awareness has led to a more careful tone in recent work. Claims are framed with uncertainty. Results are presented as ranges rather than absolutes. Comparisons are made using matched samples and shared assumptions wherever possible. The language has softened not because the science is weaker, but because it is more honest. There is also a subtle shift in emphasis. Instead of asking which galaxy is bigger, astronomers increasingly ask how similar they are. Both are large spiral galaxies. Both possess extensive halos. Both dominate their local environments. Both likely formed through comparable processes, even if the details differ. In that sense, Andromeda and the Milky Way are less rivals and more variations on a theme. There is even a touch of gentle humour in how the comparison has evolved. After decades of arguing over which galaxy holds the title of largest in the local group, the most careful analyses suggest that the answer may simply be that they are much alike, separated more by perspective than by scale. That conclusion does not diminish Andromeda's grandeur, it reframes it. Understanding Andromeda's size helps clarify our understanding of the Milky Way as well. Each measurement informs the other. Each revision sharpens the picture of what large spiral galaxies can be. The real lesson lies in the process. As methods improved, conclusions changed. As data sets expanded, confidence became more measured. As assumptions were aligned, differences narrowed. This is not indecision. It is refinement. Andromeda may still edge ahead in some measurements. The Milky Way may surpass it in others. The exact ranking is less important than the realization that size, in astronomy, is not a single quantity waiting to be declared. It is a collection of perspectives. Seen this way, comparing Andromeda and the Milky Way becomes less about contrast and more about context. Two galaxies of comparable scale, sharing space, sharing history, and teaching astronomers the same quiet lesson. How you measure determines what you see. Andromeda's influence does not stop with its stars. Long after the bright spiral disk fades from view, and even beyond the faint stellar halo, the galaxy continues to shape its surroundings. Not through light, but through gravity. The slow, persistent kind that leaves its mark over immense spans of time. One of the clearest signs of this influence comes from the small galaxies that orbit Andromeda. These satellite galaxies are scattered across a wide region of space, each moving along a path determined largely by Andromeda's mass. Some are compact and dense, others are diffuse and fragile, barely holding together. All of them are bound, not by chance, but by gravity acting patiently over billions of years. As astronomers mapped these satellites more completely, a pattern emerged. They were not confined to the immediate vicinity of the bright disk. Many orbited at vast distances, hundreds of thousands of light-years away. Some followed elongated paths, venturing far out before slowly curving back in. To remain bound on such wide orbits, Andromeda's gravitational reach had to be enormous. Each satellite's motion provides a clue. By measuring how fast it moves and how far it strays, astronomers can estimate how much mass lies within its orbit. Again and again, the same conclusion appears. Andromeda's influence extends far beyond what its visible stars would suggest. But satellites are not the only evidence. Scattered throughout the space around Andromeda are faint stellar streams, long, thin ribbons of stars stretching across the sky, sometimes looping gracefully, sometimes twisting irregularly. These streams are the remnants of smaller galaxies that wandered too close and were slowly pulled apart. They are not violent scars, they are gentle records. As a smaller galaxy falls into Andromeda's gravitational field, tidal forces begin to act. Stars on the near side feel a stronger pull than those on the far side. Over time, this difference stretches the galaxy, peeling stars away and spreading them along its orbit. What remains is a stream tracing the path of the encounter. These streams are extraordinarily useful. They act like test particles, outlining the shape and strength of Andromeda's gravitational field. By following their paths, astronomers can infer how mass is distributed throughout the region. Where the stream bends, gravity is guiding it. Where it thins, time has been at work. Some of Andromeda's streams extend hundreds of thousands of light-years. Their very existence shows that the galaxy's influence reaches at least that far, and often farther. A stream cannot persist outside the region where gravity still holds sway. In this way, Andromeda's territory becomes visible, even though it does not shine. This territory is not a fixed boundary. It is a zone of influence, a region where objects move in response to Andromeda's mass rather than drifting freely through space. Within it, motion is organized. Outside it, other gravitational players begin to matter more. Importantly, all of this happens very slowly. Satellite galaxies do not whip around Andromeda in short loops. Their orbits can take billions of years to complete. Stellar streams form gradually, stretching over time as gravity does its work with steady restraint. Nothing here is rushed. Cosmic motion is unhurried. This slowness is easy to underestimate. When looking at images, it is tempting to imagine dramatic events unfolding quickly. In reality, even major changes play out at a pace that makes stillness seem like action. Andromeda's influence grows not through sudden expansion, but through accumulation. Each merger adds mass. Each captured satellite extends the reach of gravity. Each stream marks a chapter in a history written over unimaginable durations. From this perspective, the galaxy's visible body is almost misleadingly small. The bright disk marks where stars are concentrated and active. The stellar halo shows where stars are sparse but still present. Beyond both lies a much larger domain defined not by what can be seen, but by what can be held. This domain includes satellites still intact, streams in the process of dissolving, and debris long since spread thin. All of it responds to Andromeda's gravity. All of it belongs, in a meaningful sense, to the galaxy. There is also an important subtlety here. Andromeda's territory is not exclusive. In the vastness of space, gravitational domains can overlap. The outer reaches of Andromeda's influence blend with that of the Milky Way, and other members of the local group. In these regions, no single galaxy dominates completely. Instead, gravity becomes a shared language. Objects move under the combined influence of multiple masses. Their paths curve gently, shaped by a balance rather than a single pull. The idea of ownership gives way to interaction. Still, within its immediate environment, Andromeda is unmistakably dominant. Its satellites align broadly around it. Its streams arc through space in coherent patterns. Its mass sets the tempo of motion across a huge volume. Even far from the bright disk, the galaxy's presence is felt. This understanding changes how size is perceived. Asking how far Andromeda's influence reaches is different from asking how large it looks. One question is about appearance, the other is about effect. The first stops where light fades, the second continues until gravity weakens enough to yield control. By that second measure, Andromeda is immense. Its territory encompasses a region far larger than its visible form, a space shaped over billions of years by slow mergers, gentle tides, and steady motion. A domain where stars and galaxies move not randomly, but in quiet response to a massive neighbour. There is a certain elegance in this arrangement. Nothing here announces itself loudly. No sharp borders declare ownership. Influence tapers. Control softens. Motion slows. The galaxy's reach is revealed only through patience and careful observation. Andromeda does not claim space with brightness. It holds it with gravity. Understanding this reach brings a calmer perspective to cosmic scale. Galaxies are not isolated islands floating in emptiness. They are participants in a shared environment, their influences overlapping and interacting over immense distances. Andromeda's influence reaches far, not because it is aggressive, but because it has existed for a very long time. Given enough time, even a gentle pull can shape an enormous volume. That is the quiet power of a galaxy. When Andromeda is observed, it is never seen as it is now. The light arriving at Earth left the galaxy more than 2 million years ago. Every photon began its journey long before modern humans existed, long before recorded history, long before the landscapes of Earth looked anything like they do today. What reaches telescopes tonight is a message from deep time, carrying information that has been travelling patiently through space for longer than any human story. This simple fact changes how size must be understood. Measurements of Andromeda do not describe a present moment frozen in place. They describe a snapshot from the distant past. The disk, the halo, the streams and the satellites are all seen as they were more than 2 million years ago, not as they are now. The galaxy may have changed since then, subtly, slowly, but meaningfully. On human timescales, 2 million years feels impossibly long. On galactic timescales, it is a brief pause. Stars take hundreds of millions to billions of years to complete orbits. Galaxies grow through mergers that unfold over enormous spans of time. Structures evolve gradually, shaped by gravity acting with steady persistence. In that context, Andromeda has not transformed dramatically in the time its light has been travelling toward us. But it has not stood still either. This introduces a quiet complication. When astronomers measure Andromeda's size, they are measuring a historical version of the galaxy. The extent of its disk reflects where stars were distributed in the past. The reach of its halo shows where ancient stars had already wandered. The paths of stellar streams reveal interactions that may no longer be actively unfolding. Size, in other words, is time-stamped. This becomes especially important when discussing the galaxy's outskirts. The faintest regions, the ones that define its greatest extent, are often the oldest. Halo stars formed early. Streams record events long completed. These structures evolve slowly, but they do evolve. Some stars drift farther out. Some streams stretch and thin. Some satellites lose material over time. the Andromeda seen today may be slightly more extended, slightly more diffuse than the Andromeda whose light now reaches Earth. Astronomers account for this by turning to simulations. Using the laws of gravity and well-tested models of cosmic evolution, researchers simulate how galaxies like Andromeda grow and change over billions of years. These simulations incorporate mergers, star formation, and the slow redistribution of matter. They are not predictions in the everyday sense. They are controlled experiments, asking what kinds of histories produce galaxies like the one observed. When simulations are matched to Andromeda's current appearance, they suggest a gentle trajectory of growth. The galaxy is expected to continue expanding its halo gradually as it absorbs small companions and redistributes stars. Its dark matter halo slowly adjusts as mass accumulates. Its visible disk evolves modestly, shaped by ongoing star formation and internal motion. None of this is abrupt, none of it is dramatic. The simulations indicate that Andromeda's overall size changes slowly, measured in tens or hundreds of millions of years rather than in moments. Over the 2 million years represented by the light now arriving, the galaxy would have changed only slightly. Enough to matter scientifically, but not enough to invalidate observation. Still, this delay introduces uncertainty. When astronomers say Andromeda's halo extends a certain distance, they are describing where stars were, not where they are now. When they estimate the reach of its gravitational influence, they are working from motions observed in the past. The present-day galaxy exists just beyond direct observation, inferred rather than seen. This does not weaken the conclusions. It clarifies their meaning. Astronomy is always an exercise in patience. The universe does not offer real-time updates. It communicates through delayed signals, and astronomers learn to interpret them with care. Measurements are understood as time-averaged, not instantaneous. In fact, this time delay can be an advantage. By observing Andromeda as it was, astronomers gain insight into its history. The structures visible today are the result of long processes already completed. Streams show where mergers occurred. Halo stars reveal early conditions. The galaxy's size encodes its past more clearly than its present. There's also a gentle irony here. The farther out astronomers look, the further back in time they see. The outermost regions of Andromeda are not just spatially distant, they are temporally distant as well. They carry information from earlier stages of the galaxy's evolution. Size and time become intertwined. The larger structures often preserve the older stories. The faint halo stars tell of formation epochs long gone. The extended streams trace interactions that may no longer be ongoing. The dark matter halo reflects the cumulative history of growth across billions of years. Understanding Andromeda's size, then, is partly an exercise in historical reconstruction. Astronomers compare what is seen to what simulations suggest should exist at different stages of evolution. They adjust models to match observations. They test whether the galaxy's present appearance is consistent with known physical processes. In doing so, they accept uncertainty as part of the picture. No measurement claims to capture Andromeda exactly as it is at this instant. Instead, each describes a version of the galaxy close enough to be meaningful, shaped by a small and well-understood delay. There is something quietly comforting in this limitation. It reminds us that the universe is not rushing. Galaxies evolve slowly. Changes unfold over timescales that dwarf human experience. Even when looking millions of years into the past, the picture remains broadly accurate. Andromeda's size, however defined, is not fleeting. It is stable on timescales far longer than civilizations. The galaxy grows and changes, but it does so with remarkable restraint. This perspective also softens the idea of precision. When astronomers speak of Andromeda's extent, they are not chasing a single exact number. They are describing a range that makes sense given time delays, observational limits, and slow evolution. That range is robust even if the present-day galaxy differs slightly from what is seen. The light arriving now is old, but it is not misleading. It tells a truthful story about scale, structure, and influence. It just does so with a gentle temporal offset, reminding us that knowledge in astronomy always arrives after the fact. Seeing Andromeda across time reframes the question of size once more. The galaxy is not a static object waiting to be measured precisely. It is a living system, evolving slowly, its past continually visible, its present inferred, its future explored through simulation. What we measure is not moment, it is a history. And in that history, Andromeda has been large for a very long time. For anyone following the story of Andromeda over time, one detail can feel oddly unsettled. The numbers keep changing, its size is revised, its mass is updated, its extent stretches, then steadies, then stretches again. At first glance, this can feel uncomfortable. Surely a galaxy either has a certain size or it does not. But in astronomy, changing numbers are not a sign of confusion. They are a sign that measurement is becoming more precise. Size estimates change because the data improve. For much of the 20th century, astronomers worked with limited information. Distances were uncertain. Motions were difficult to measure. Many conclusions rested on indirect indicators and careful inference. These methods were not careless or crude. They were the best tools available at the time. As instruments improved, those tools became sharper. One of the most significant advances came from missions designed to measure positions and motions of stars with extraordinary accuracy. By tracking how stars shift against the distant background as Earth moves around the Sun, astronomers can determine distances directly. They can also measure how stars move through space, not just along the line of sight but sideways as well. This is where missions like Gaia change the landscape. Gaia mapped the positions, distances and motions of more than 1 billion stars in the Milky Way and beyond. For Andromeda, its contribution was subtle but profound. While Gaia cannot measure individual distances to most Andromeda stars directly with the same precision as nearby stars, it dramatically improved the calibration of distance indicators and the understanding of stellar motion in the local group. Better distances ripple outward into better size estimates. When the distance to Andromeda is refined, even slightly, every measurement tied to that distance adjusts. The physical size of the disk changes, the scale of the halo shifts, the inferred mass distribution responds accordingly. What once seemed like a small revision can reshape multiple conclusions at once. This is not correction in the everyday sense, it is refinement. Earlier astronomers were not wrong to work with the numbers they had. Their estimates were constrained by the data available. As new information arrives, conclusions are updated to reflect a clearer picture. The earlier work remains valid within its original limits. This process is visible throughout Andromeda's story. Early measurements focused on the bright disk because that was what could be seen. Later observations revealed the halo. Still later, improved motion data reshaped mass estimates. Each stage added depth rather than overturning what came before. Think of it like adjusting the focus on a lens. The object does not change, the clarity does. Better data also reduce uncertainty in subtle ways. Instead of producing a single number, astronomers often narrow the range within which that number likely falls. A disk size might not be revised dramatically, but confidence in that size increases. A mass estimate may shift slightly, but the error bars shrink. Over time, the picture becomes more stable, even if individual values continue to evolve. Motion measurements play a particularly important role here. As astronomers gain more precise information about how stars and satellite galaxies move, they can infer mass distributions more accurately. Small errors in velocity can lead to large differences in mass estimates, especially at great distances. Improving those measurements reshapes the inferred gravitational structure. This is why size and mass estimates are often revised together. They are linked through motion. There is also an important cultural aspect within astronomy that shapes how these changes are handled. Scientists are cautious by design. New results are compared against existing ones. Discrepancies are examined rather than celebrated. When a new estimate differs from an older one, the question is not which is right, but why they differ. Is the data set larger? Is the method improved? Are the assumptions more realistic? Only after this careful comparison do conclusions shift. This approach prevents dramatic swings based on limited evidence. It ensures that revisions are incremental, grounded, and well understood. When Andromeda's size estimates change, they do so gradually, guided by accumulating evidence rather than sudden reinterpretation. There is also a reassuring pattern to these revisions. Each improvement in measurement tends to add complexity rather than remove it. Andromeda has not become simpler with time, it has become more layered, more extended, more nuanced. That consistency suggests the underlying picture is converging, even if the details continue to sharpen. Changing numbers in this context are not moving targets, they are tightening estimates. It is worth remembering that astronomy deals with extraordinary scales. Small percentage changes can correspond to hundreds of thousands of light years. What looks like a large revision on paper may represent a modest adjustment relative to the galaxy's full extent. This can make progress feel noisy when it is in fact steady. There is also a human element to all of this. Astronomers are careful not to overstate certainty. When new data arrive, they resist the urge to declare final answers. Instead, they integrate the information, update models, and communicate results with appropriate restraint. This can give the impression that the science is unsettled, when in reality it is becoming more robust. Andromeda's size has not been bouncing randomly over time. It has been expanding in understanding as new components are revealed and old assumptions refined. Each revision has moved the picture closer to reality, even if that reality remains complex. There is a quiet maturity in this process. Science does not advance by erasing the past. It advances by building on it. Earlier work provided the foundation that made later discoveries possible. Without initial disk measurements, there would be no baseline for halo expansion. Without early mass estimates, there would be no context for dark matter halos. Every stage depends on the ones before. This perspective reframes changing numbers as a success story. They show that instruments are improving, that methods are becoming more consistent, that models are being tested against richer data sets. They also show restraint. Astronomers do not rush to simplify a galaxy that is inherently complex. They accept that some uncertainty will remain, especially at the larger scales. They refine what can be refined and leave open what cannot yet be settled. In the case of Andromeda, this means size estimates will likely continue to adjust, but within narrowing bounds. The disk is well characterized. The stellar halo is mapped with increasing confidence. The dark matter halo is constrained by growing data sets and improved simulations. The broad picture is stable, even as the details sharpen. There is even something quietly encouraging in watching the numbers change. Each update represents another step toward understanding something unimaginably large, distant, and subtle. It is evidence that the tools are working. Changing estimates do not mean astronomers are unsure what Andromeda is. They mean astronomers are learning how to describe it more accurately, and that learning is ongoing. In astronomy, certainty is not a fixed point. It is a direction, and with each refinement the view becomes clearer, calmer, and more complete. Imagine being inside Andromeda, not rushing, not falling, simply present within it. Despite how it is often depicted, the galaxy would not feel crowded. There would be no glowing traffic of stars passing close by, no dense walls of light pressing in from every direction. In fact, the most striking feature would be space. Vast, quiet space. Astronomers know this because star density inside Andromeda has been measured carefully. By counting stars in small regions and scaling outward, it becomes clear that even within the bright spiral disk, stars are separated by enormous distances. Typical spacing between stars is measured in light years, not in fractions of a year, not in months, but in the distance light travels over multiple years. That spacing remains surprisingly consistent. Even in the denser parts of the disk, stars are usually several light-years apart. In the spiral arms, where stars are somewhat more concentrated, the distances shrink slightly, but not enough to feel enclosed. You could travel for years at the speed of light and still pass nothing but darkness between one star and the next. This alone dissolves one of the most common myths about galaxies. They look dense because their light is compressed into an image. Millions or billions of stars are projected onto a flat surface, stacked visually on top of one another, but depth is lost in that compression. In reality, those stars are scattered through three-dimensional space, separated by distances so large that the galaxy feels more like a fog than a crowd. If you were inside Andromeda, most directions would appear dark. Stars would be points of light rather than walls of glow. The sky would be filled with pinpricks, not floods. Even near the central regions where star density increases, the feeling would remain open and spacious. Measurements of stellar density confirm this calm arrangement. Astronomers estimate the number of stars per cubic light-year in different regions of the galaxy. Even in Andromeda's core, where stars are more tightly packed, the average separation is still measured in tenths of a light-year, not in astronomical closeness. Outside the core, distances grow rapidly. In the spiral disk, the environment would feel broadly similar to the neighbourhood of our own Sun. Wide gaps, long silences, occasional brilliance surrounded by darkness. Moving outward into the stellar halo, the sense of space becomes even more pronounced. Halo stars are sparse by design. They occupy a vast volume with enormous distances between them. You could drift for tens or hundreds of light years without encountering another star. This sparsity is not emptiness. It is structure at a different scale. The halo exists not because stars are numerous there, but because gravity holds them together across long distances. Their presence is subtle, but meaningful. Each star traces the galaxy's mass, even when it contributes little light. From within, Andromeda would not announce its size through density. It would do so through extent. No matter which direction you looked, there would always be more space beyond the next star. The galaxy would feel boundless, not because it is filled, but because it is spread out. There is also a quiet regularity to this arrangement. Stars orbit the galaxy's centre on long, slow paths. Their motions are gentle. Collisions between stars are extraordinarily rare. In most regions, they are effectively impossible over the lifetime of the universe. The galaxy is dynamic but not chaotic. This is another myth worth setting aside. Galaxies are not turbulent swarms. They are slow systems, governed by gravity acting patiently. Inside Andromeda, change happens gradually. Orbits evolve over hundreds of millions of years. Structures shift over billions. If you were to remain in one place for a human lifetime, almost nothing would appear to move at all. Even the densest star clusters within Andromeda offer more space than intuition expects. Globular clusters pack stars closer together than the surrounding disk, but even there, the distances are vast compared to everyday experience. These clusters are exceptions, not the rule. Most of the galaxy is quiet. The second-person perspective helps clarify this. You would not feel surrounded. You would feel suspended, embedded within a structure defined more by absence than presence. Light would arrive from all directions, but gently diluted by distance. The galaxy's immense star count does not translate into congestion. 1,000,000,000,000 stars spread across such a large volume produce a remarkably sparse environment. Scale does the work. This spaciousness is essential to how galaxies function. If stars were packed closely together, gravitational interactions would disrupt orbits and destabilize systems. The calm spacing allows galaxies to persist for billions of years without tearing themselves apart. Stability emerges from distance. There is even something quietly reassuring in this. Despite its immense size, Andromeda is not overwhelming from the inside. It does not press in. It does not crowd. It offers room to exist. Visualizing this correctly requires letting go of familiar imagery. No swirling tunnels of light, no dense clouds of stars brushing past. Instead, a wide, open expanse punctuated by occasional brilliance. Star density data supports this image at every scale. As you move from the core to the disk, from the disk to the halo, the trend is always the same. Density falls, space increases, the galaxy fades rather than fills. This fading does not diminish Andromeda's presence, it defines it. Inside the galaxy, size is felt not through pressure, but through patience, through the knowledge that even after travelling immense distances, you would still be within its gravitational embrace. The calmness of this environment stands in contrast to how galaxies are often imagined. Andromeda is not a place of constant motion and collision. It is a place of long orbits, gentle tides, and quiet persistence. Seen from within, the galaxy's true character becomes clear. It is large, not because it is crowded, but because it is extended. It is impressive, not because it is loud, but because it is spacious. And within that space there is room enough for time to pass slowly. When Andromeda is placed among other galaxies, its size becomes easier to understand. On its own, the galaxy feels immense. Its disk spans hundreds of thousands of light years. Its halo reaches far beyond what the eye can trace. Its gravitational influence stretches across a large portion of the local group. But size in the universe is rarely absolute. It is almost always relative. Astronomers have studied thousands of spiral galaxies across a wide range of environments, from isolated systems drifting alone to crowded clusters where interactions are common. When Andromeda is compared using the same measurement techniques applied to these galaxies, a clear picture emerges. It is large, but it is not unusual. Surveys that catalogue spiral galaxies by disk size show a broad distribution. Many spirals are smaller than Andromeda, with compact disks and modest halos. Others are larger, extending farther and containing even more stars. Most fall somewhere in between. Andromeda sits toward the upper end of this distribution, but not at the extreme edge. Its disk is broader than average, but not exceptional. Its stellar halo is extensive, but comparable to those of other large spirals that have undergone similar histories of growth and merger. Its total mass places it among the heavier spirals, yet still well within the expected range. This context matters. Without comparison, Andromeda's size can feel overwhelming. With it, the galaxy becomes familiar. A large example of a common pattern rather than a singular outlier. Statistical studies of galaxy populations reveal that spiral galaxies span a wide range of sizes, but they follow recognizable trends. Disk size correlates loosely with mass. Halo extent reflects merger history. Star count scale with both formation efficiency and available material. Andromeda fits these trends comfortably. Its size reflects a long but not extreme growth history. It has absorbed smaller galaxies, but not in unusually large numbers. It has formed stars steadily, but not at rates that would place it far outside the norm. Its structure looks exactly like what astronomers expect from a massive spiral that has had time to mature. This realization reframes the question of size once again. Andromeda feels enormous not because it is unique, but because spiral galaxies themselves are enormous. The Milky Way shares this scale, so do many others scattered throughout the universe. What feels extraordinary is not Andromeda specifically, but the category it belongs to. There is also an important selection effect at work. Large galaxies are easier to study, they are brighter, their structures are more pronounced, their halos are more readily traced. Smaller galaxies, especially faint ones, are harder to detect and characterize. This can skew intuition, making large spirals feel more common or more significant than they are. When astronomers account for this bias, the picture becomes clearer. Most galaxies in the universe are actually smaller than Andromeda. Dwarf galaxies are far more numerous. They contain fewer stars, extend over shorter distances, and exert more limited gravitational influence. Against this backdrop, Andromeda stands out as a heavyweight, but not as an anomaly. It is simply a mature spiral in a universe that produces many such systems. Comparisons also highlight how definition shapes perception. If size is defined by visible disk diameter, Andromeda ranks high, but not at the top. If size is defined by stellar halo extent, it again appears large, but still within expected bounds. If size is defined by dark matter halo reach, the uncertainty grows, but Andromeda remains consistent with other galaxies of similar mass. Each definition places it in a slightly different position within the distribution, but none isolate it as extreme. This reinforces an important idea. There's no single ranking that captures what it means for a galaxy to be big. Different measures emphasize different aspects of structure. When those measures are applied consistently, Andromeda behaves exactly as it should. There is a quiet comfort in this consistency. The galaxy that once seemed to stretch endlessly outward turns out to be a well-behaved member of a larger population. Its vastness does not require special explanation. It emerges naturally from the same processes that shape countless other spirals: growth through merger, accumulation of dark matter, long-lived star formation. These are common mechanisms. Andromeda simply represents their outcome on a generous scale. Even its environment reflects this normalcy. Andromeda resides in a modest group of galaxies, not a dense cluster. This has allowed it to grow without frequent disruptive encounters. Many large spirals in similar environments show comparable sizes and structures. The absence of extreme crowding has preserved its disk and allowed its halo to expand gently over time. Again, nothing unusual is required. This perspective also tempers earlier narratives that framed Andromeda as a dominant giant. It is dominant locally, yes, but cosmically it is one of many. Its size is impressive, but not singular. Its influence is strong, but not unrivaled. Understanding this does not diminish Andromeda, it places it properly. Relational scale is the key. A galaxy's size means little in isolation. It gains meaning only through comparison. Against smaller dwarfs, Andromeda is enormous. Against the largest known spirals, it is moderate. Within the broad family of mature spirals, it feels at home. This relational view also helps resolve lingering questions about measurement. When size estimates change slightly, Andromeda does not jump wildly within the distribution. It shifts gently, remaining within the same general range. That stability suggests the underlying understanding is sound, even as details are refined. There is also a subtle lesson here about perspective. From Earth, Andromeda feels special because it is close. It dominates the night sky in a way distant galaxies do not. That proximity makes its scale easier to sense and harder to contextualize. When placed among thousands of others, its familiarity becomes an asset rather than a distortion. It serves as a reference point. Astronomers often use Andromeda as a benchmark when studying spiral galaxies. Its size, mass, and structure provide a concrete example against which others can be compared. In this role, its normalcy is precisely what makes it valuable. A galaxy that behaved oddly would be less useful. So Andromeda's size, when viewed broadly, tells a reassuring story. It confirms that the processes shaping galaxies operate consistently across the universe. It shows that large spirals are not rare accidents, but natural outcomes of cosmic evolution. The galaxy does not stand apart from the universe, it fits within it. Seen this way, Andromeda's vastness feels less like an exception and more like a pattern. One instance of a common theme, expressed on a grand scale. It is large, yes, but it is large in the way many galaxies are. And that makes its size not just impressive but understandable. The future size of Andromeda is not something that will arrive suddenly. It will unfold slowly, almost imperceptibly, over spans of time that resist everyday intuition. Astronomers explore this future using simulations, not predictions in the sense of forecasting an event, but careful reconstructions of how galaxies evolve when gravity is allowed to act over billions of years. These simulations begin with what is known today: the distribution of stars, the extent of dark matter, the motions of satellites. From there, the clock is allowed to run forward. What emerges is not a story of abrupt change, but of steady growth. Galaxies like Andromeda increase in size primarily through mergers. Small galaxies drift nearby, become gravitationally bound, and are slowly absorbed. This process is neither violent nor fast. A merger can take billions of years from beginning to end, with most of that time spent in gradual adjustment rather than disruption. The first components to interact are not the bright disks, they are the halos. Dark matter halos extend far beyond visible stars, and they are the first regions to overlap when galaxies approach one another. Long before stars respond, the invisible structures begin to merge, blending smoothly and redistributing mass across a larger volume. This happens quietly. As halos merge, the combined gravitational field becomes more extensive. The effective size of the system grows, even if nothing dramatic appears to be happening. Stars continue their orbits. Disks remain intact. The change is real but subtle. Simulations consistently show this pattern. Halo growth leads. Visible structure follows later, if at all. For Andromeda, this means that its future size will likely increase gradually as it continues to absorb smaller companions. Each merger adds stars to the outskirts, extending the stellar halo. Each addition slightly reshapes the dark matter distribution, increasing gravitational reach. None of this resembles a collision in the everyday sense. There are no sudden impacts, no sharp boundaries crossing. Instead, there is a long period of mutual influence, stretching and redistributing material with gentle persistence. Even when galaxies eventually share visible stars, the process is drawn out and calm. Time does the work. Simulations suggest that Andromeda's halo will continue to grow for billions of years, becoming more extended and more diffuse. Its visible disk may change only modestly, maintaining its general structure while slowly evolving internally. The most dramatic changes remain confined to the faint outskirts. This reinforces a theme that has appeared repeatedly. The parts of a galaxy that grow the most are often the parts that shine the least. It is also worth noting how slow this growth truly is. On the scale of human history, nothing noticeable will happen. On the scale of civilizations, the galaxy will appear unchanged. Even on the scale of millions of years, the differences will be subtle. Only when measured across billions of years does the accumulation become clear. This slowness is not a limitation. It is a feature. Galaxies persist because change is gradual. Their structures are not fragile. They are resilient, shaped by long-term balance rather than short-term disturbance. Andromeda's future size reflects this stability. There is sometimes a temptation to frame the future of Andromeda in dramatic terms, to imagine sudden encounters or decisive moments. But the reality, as revealed by simulations, is quieter. Growth is continuous. Boundaries soften, influence spreads, halos blend long before disks respond. By the time visible structures interact, the gravitational relationship has already been established for a very long time. The system has been evolving as one for ages. This perspective changes how the future is understood. Andromeda is not heading toward a single defining event that will suddenly make it larger. It is already becoming larger, slowly, through processes that began long ago and will continue far into the future. The galaxy's size, then, is not a static property waiting to be updated. It is a trajectory. Each merger adds a layer, each redistribution extends reach. Each passing billion years smooths the structure further. Even simulations that explore far futures show this same restraint. The overall shape evolves, but the system remains recognizable. The galaxy does not explode into chaos. It adapts. There is even a certain quiet humor in this. After all the effort to measure Andromeda's size precisely, the future suggests that the answer will never stop changing. Not because the measurements are flawed, but because the galaxy itself is still in the process of becoming. This does not make the present understanding obsolete. It places it in context. Astronomers measure Andromeda's size as it is now, knowing that now is part of a continuum. The values are meaningful snapshots, not final statements. They capture a stage in a long, slow evolution. The future size of Andromeda will be larger than today's estimates suggest, but it will arrive gently, layered atop what already exists. No sudden transformation will announce it. In the end, Andromeda's growth is not about expansion into emptiness. It is about incorporation, drawing in what is already nearby, sharing gravitational influence, becoming more extended through patience rather than force. Measured in billions of years, the galaxy will grow. Measured in moments, it will appear still. That contrast is at the heart of galactic evolution. Andromeda's future size is not something to wait for. It is something already underway. By the time Andromeda has been examined from every angle, one quiet realization settles in. Size in astronomy is not a single thing. It is not a number waiting to be discovered and written down. It is not a boundary that can be drawn with confidence and left unchanged. Instead, size depends on what is being asked, how it is measured, and which aspect of a system is being considered. Andromeda taught astronomers this lesson slowly. At first, size meant brightness, how wide the glowing disk appeared against the night sky, how far spiral arms could be traced before they faded into darkness. This was a natural starting point. Light is what telescopes see most easily. It offers structure, contrast, and shape. But brightness turned out to be a guide, not a definition. As observations deepened, size began to include faint stars beyond the disk. Halo stars stretched the galaxy outward, revealing that what appeared complete was only the most visible layer. Size expanded again, not because the galaxy changed, but because understanding did. Then gravity entered the conversation. When astronomers measured motion, size took on a new meaning. The reach of a galaxy could be inferred not by where stars shone, but by how far its mass influenced movement. Satellite galaxies, stellar streams, and velocity patterns all pointed to a much larger domain, one that could not be photographed directly. Here, size meant influence. Andromeda's gravitational reach extended far beyond its visible form, reshaping how astronomers thought about where a galaxy truly ends. The idea of a clean edge began to dissolve. Instead of borders, there were gradients. Instead of lines, there were transitions. Theory added another layer still. Simulations showed how galaxies grow over time, how halos merge before disks, how mass redistributes slowly across billions of years. From this perspective, size was no longer a static property. It was a stage in an ongoing process, a moment along a trajectory. Each definition was valid. None was complete on its own. Observational size describes what can be seen. Gravitational size describes what can be felt. Theoretical size describes what emerges over time. Together they form a fuller picture. Andromeda sits at the intersection of all three. Its bright disk gives a sense of structure. Its stellar halo reveals history. Its dark matter halo defines influence. Its future growth places all of this within a long continuum. What this teaches is not just something about Andromeda, but something about astronomy itself. Measurements do not converge on a single truth by accident. They do so by context. When astronomers specify how size is defined, their conclusions become clear and consistent. When definitions are mixed, confusion arises. Andromeda was once described as growing larger with every new study. In reality, understanding was growing larger. Each method revealed a different aspect of the same system. There is a gentle humility in this realization. Astronomy deals with objects so vast that no single perspective can capture them fully. Light offers one view, motion offers another, models offer a third. Each reveals something the others cannot. Andromeda, by refusing to fit neatly into one definition of size, helped make this clear. It also softened the idea of precision. Rather than chasing a single definitive measurement, astronomers learned to describe size in terms of ranges, contexts, and relationships. A galaxy can be this wide in light, that extensive in gravity, and larger still in theoretical reach. All of these statements can be true at the same time. This approach does not weaken understanding, it strengthens it. There is also a shift in emotional tone that comes with this broader view. Once size is no longer treated as a fixed answer, the urgency to pin it down fades. What remains is appreciation for scale, structure, and process. Andromeda becomes less of a problem to solve and more of a system to understand. The galaxy is large in ways that matter differently depending on where attention is placed. It is large in star count, large in extent, large in influence, large in history. None of these qualities cancels the others. They layer together. Even uncertainty takes on a different character. Uncertainty is not a gap in knowledge waiting to be closed. It is a measure of how complex the system is. Where boundaries blur, astronomy responds not by forcing clarity, but by refining questions. Andromeda's size remains slightly uncertain at its furthest edges because the galaxy itself does not offer a sharp stopping point. Its influence fades, its stars thin, its gravity blends with that of its surroundings. This is not a failure of measurement, it is a property of galaxies. The lesson extends beyond Andromeda. Every galaxy, when examined closely enough, behaves in the same way. Bright centers give way to faint outskirts. Clear structures dissolve into diffuse halos. Influence stretches farther than light. Size becomes relational rather than absolute. Andromeda simply happened to be close enough, large enough, and well studied enough to make this lesson unmistakable. There is also something quietly reassuring here. The universe does not demand perfect definitions. It allows for softness at the edges. It permits overlap. It tolerates ambiguity. Understanding deepens not by eliminating this ambiguity, but by learning to work within it. For Andromeda, this means that asking how big it is will always depend on the lens through which the question is asked. The answer shifts gently with context, not because the galaxy is elusive, but because it is rich. As this realization settles, the question of size begins to feel less urgent. What matters more is what size reveals, about formation, about motion, about time, about how matter organizes itself across immense distances. Andromeda is large not just in scale, but in what it teaches. It shows how galaxies are layered systems rather than simple shapes. It demonstrates that influence matters as much as appearance. It reminds astronomers that measurements improve by adding perspectives, not by replacing them. In the end, size in astronomy is not about drawing a line and declaring completion. It is about understanding relationships between stars and space, between light and gravity, between present appearance and long history. Andromeda holds all of these relationships at once. As the focus begins to soften, the galaxy no longer feels like an object to be measured from the outside. It feels like an environment, extended, layered, and patient. Its size is not a single answer. It is a quiet collection of truths, and that understanding carries naturally forward toward reflection rather than resolution, where the need to define gives way to the freedom to observe. So, how big is the galaxy we call Andromeda? By now, the answer feels less like a single number and more like a layered understanding. The galaxy has a bright spiral disk that can be measured and traced with care. It has a vast halo of stars extending far beyond that disk. It has an even larger gravitational presence, shaped by mass that cannot be seen directly. And it has a future size still unfolding, changing slowly as time continues its quiet work. All of these answers are true at once. Andromeda is measurable. Astronomers can estimate its diameter, its mass, its star count, and the reach of its influence. Those measurements are grounded in observation, motion, and careful modelling. They are not guesses. They are the result of decades of patient work refined again and again as better data becomes available. And yet Andromeda is also open-ended. Its edges fade rather than stop. Its influence blends into the surrounding space. Its most distant components resist sharp definition. Even its present form is seen through a window of time, shaped by light that began its journey millions of years ago. This combination of clarity and openness is not a flaw in understanding. It is what understanding looks like at cosmic scale. In everyday life, uncertainty often feels like a problem to be solved. In astronomy, uncertainty is often a sign that the questions being asked are appropriately large. When dealing with galaxies, clean boundaries are rare. Gradients, overlaps, and slow transitions are the rule rather than the exception. Andromeda demonstrates this beautifully. Each attempt to define its size revealed something new. Light showed structure. Faint stars revealed history. Motion uncovered hidden mass. Simulations added time. None of these erased what came before. They added context. The galaxy did not become more confusing as knowledge grew, it became richer. There is something quietly reassuring in this process. It shows that understanding does not require final answers. It requires careful framing. When astronomers say how large Andromeda is, they are not claiming completeness. They are describing the galaxy from a particular perspective, with a particular set of tools. That perspective can change. The galaxy remains. From Earth, Andromeda appears as a calm glow in the night sky. It does not advertise its scale. It does not demand attention. Its vastness is subtle, revealed only through patience and perspective. This subtlety is part of its lesson. The universe is full of structures that are larger than our intuition allows, yet gentle in their expression. Size does not always announce itself with brightness or drama. Sometimes it reveals itself through quiet accumulation, through faint stars counted carefully, through motions traced over long spans of time. Andromeda reminds us that scale in the universe is not about spectacle. It is about context. Placed among other galaxies, it is large but not extreme. Seen from within, it is spacious rather than crowded. Viewed across time, it is stable yet slowly evolving. Considered through gravity, It is expansive beyond what light alone can show. All of these views coexist. As this understanding settles, the original question softens. How big is Andromeda becomes less of a demand for precision and more of an invitation to perspective. The galaxy is large in the ways that matter for stars, for motion, for history, and for time. And it has been so for a very long while. There is no need to rush toward a final definition. The universe does not require one. It allows size to remain relational, layered, and gently uncertain. That uncertainty is not a gap waiting to be closed. It is space. Space for refinement, space for discovery, space for calm reflection. Andromeda will continue to be measured. Its numbers will continue to be refined. Its story will continue to unfold slowly, across billions of years. For now, it is enough to know this. The galaxy is vast, it is patient, and it is exactly as large as it needs to be. You can let that scale rest where it is. There is nothing more you need to hold on to, and the universe is in no hurry.